I'm really sorry, guys. I might have to take a few breaks in today's session because I'm not keeping well. I'm having a terrible cold here, so um, I may have to take a few seconds break in between. I may be sneezing or coughing in between. Please excuse me. So yeah, here we have 14. Okay, meanwhile, can someone tell me what you have gathered over the last week's sessions?
Ma'am, can you repeat?
Um, Please just give me an account of what you think about the last week, whatever you have learned last week. Like if you can give me a sum up or if you can say it in a nutshell, that would be great.
I can say, like in the last week, we have talked about all compact limits, compact objects and limits. For example, like neutron stars, different kinds, black holes, and then its dynamics about celestial radius and how it forms. Like what was that? LOV limit, LOV maybe limit. And I mean, in context, it can be said that we have studied about all the things that forms after a type two super after a supernova, basically. Like for before that, we studied about white dwarfs and that part. In this week, we have studied in detail about that. Then there was techniques to detect that, like gravitational lensing and transit photometry. Oh, sorry, transit photometry was for different. Uh, I mean, I don't exactly remember the exact names. Sorry about that. And in the last session, you talked about, no, before the last session, you talked about galaxies, different types of
Right.
galaxies. And for the last session, sorry, I wasn't able to attend due to some reasons. So I don't know what the last session. I haven't watched the
Yeah.
recording yet.
Yeah, no problem. Just make sure you watch the recordings over the weekend, yeah?
Okay, ma'am.
Okay. And yes, and you will be having a couple of small tasks today. Um, it's both are one day doables. So you should be able to finish it up soon. And the deadline is third Monday, because on third again, the next week we'll be dealing with our minor project too. So please don't keep this task that I'm giving you by the end of today's session. Don't keep it for next week. Try to finish it up this week because next week is going to be busy for you otherwise. Um, so yeah, I think yeah, we're almost time. I'll I'll start today's session. Yeah. Okay. So today and the next session, we'll be looking into cosmology. And we'll be looking into various aspects of cosmology. So, all about cosmology. I wouldn't say all, but some major topics. There's always a lot more when it's about astrophysics. So, some major topics will be covered, and the whole part about cosmology is divided into two: part one and part two. Today I'll be taking part one. Tomorrow you'll have part two as well. By the end of today's session, I'll be giving two assignments, and those two assignments you can look through today. Today I'll give you out, and you can look through it. If you have any doubts, you can clear it up in tomorrow's session, and then you will be submitting those assignments before our next session. So make sure tomorrow is the only time you will have to clear any or clarify any doubts about it. So make sure you look into the assignments by during the daytime tomorrow, or at least right before the session, so that you'll be able to clarify if there are any doubts. And then we'll be having the submission of those two assignments by the third, that's Monday. So I'm sure your weekend or Friday we don't have a class, so Friday one day could be enough to complete um, both the assignments, right? All right. So let's move. Uh,
Okay, ma'am.
our, is anyone trying to speak?
Vaidik.
Yes, yes. Please tell me. I guess someone was trying to speak.
Ma'am, by mistake, my mic is open.
Oh, okay, no problem, Meg. Yeah, if you don't mind, please mute it. But you can please feel free to ask any doubts, unmute yourself, and ask anything in between. Yeah, cool. All right. So let's move into today's part one of cosmology. We'll start with this one question. This is not a very technical question. It's just to see, how the general opinions are. There's no right answer. There's no wrong answer. So, if the universe is 13.8 billion years old, will the night sky look the same 100 billion years from now, or will it be empty? What do you all think, and why?
Uh,
I believe it will
I can.
look
Okay.
kind of empty because the rate at which the space between any two heavenly bodies is increasing is already greater than the speed of light. Uh,
Mm-hmm.
the reasons can be dark matter or whatever, but eventually the objects will be far apart, so we won't be able to see other objects as clearly, or it will seem like very empty sky.
Okay. Like relatively empty, you mean, right?
Empty, relatively empty.
Okay. All right. Does
Um,
anyone else
yes, ma'am.
yeah, please.
Ma'am, I would say my perspective is from the book of Stephen Hawking, in which predicted, like, after billions of years, hundreds of billions of years, the last of the neutron stars will cool off. So I think that will be the around of time of dark age, where only there will be only black holes left in the universe. So I think this night sky will be empty and plant won't
Okay.
exist.
All right. All right. Good thought. Does anyone else want to add to this?
Uh, unless there are some red dwarf stars very close by, I think what the other people said would be true. But
Red dwarf, or you mean black dwarfs or red giants?
No, red dwarfs because they have
Okay.
a very long lifespan. At
Right.
yes,
Okay. All right. Okay. Okay. Based on how many stars could still be alive by that time. So, don't you think there could be new stars formation all the time?
I mean, ma'am, as the new stars will form, there's also the ending of stars. So the stars that that ends their lifespan are more than the stars forming. So eventually, the I mean the all the things will end. That's a predicted, I mean, theory. So I have that perspective.
Yeah.
Ma'am, if
All
I
right.
would like to add on to something, I would
Yeah.
say
Please.
it would not end completely, as in
Okay.
because the dying stars are kind of fuel to some other celestial body, and the heat or the energy which is being released through each iterative um, iterative fusion or expansion, it is in an equilibrium. So somewhere when it is being sucked or synced, so somewhere it will be absorbed and regenerated. So I
Okay.
think from from now, if 100 billion years, which is nearly 113 billion years, or
Mm-hmm.
14 to be precise, it will be still going on. But the yes, what Nimit said about the expansion, I think it will be partially expanding, but
Mm-hmm.
might be possible that somewhere if the um, gravity somewhere which is being way more dominating than anything else, it might
Okay.
be a reverse of what expansion was happening. It might come together again as a single uh, ball of one singularity, or what was before the Big Bang.
Got it. All right. That's another thought. Yes. And similarly, does anyone think it could be looking the same because there's a continuous cycle happening, keeping all the other gravitational dominance or any other potential factors aside? Does anyone think it could be a continuous cycle? Maybe it look the same.
I think it will look same for like 100 millions of years, but not for billion because the billions perspective I've told. As for the millions, I think it may look same because as we already know, the universe is expanding faster than light. So the galaxies are getting apart from each other. But there is a mysterious thing that even scientists don't know about themselves. If you have heard about the Great Attractor, which
Right.
may be the reason for like future in which I mean our supercluster, which is linear supercluster, in which our two galaxies will collide, our Milky Way and the Andromeda galaxy, and the
Okay.
Great Attractor is the reason. So I think our night sky may look more bright if Earth will exist at that point of time, or like any planet we are observing from for next millions of years, but I don't think for billions of years because by that time our like universe is not in a static equilibrium
Got it. Yeah.
as per
Yeah.
the theories.
All right. So all these are different thoughts that we have, and there is no, as I've said, there are no correct answers and wrong answers. There are a lot of predictive theories, which are very similar to what you all have said about gravitational dominance, as well as the universe expanding enough to be relatively farther from each other. So nights could look extraordinarily empty as well. And so there are a lot of predictive theories. Nobody knows for sure. There are nothing, no supporting evidences. So as of now, I think there's no wrong answer and there's no right answer. So these are all just food for thought. Anyway, so we'll quickly get into our today's agenda. And so, the part one, we'll be dealing with the big picture. We'll be talking about the expanding universe, which includes various factors in it, like the Hubble's law. redshift, cosmological redshift, and cosmic scale factor. Then we'll be discussing about the universe's baby picture, as in the CMB, that is cosmic microwave background, and some inflation theory as well. That is it for today. Tomorrow we'll be dealing with part two, right? So let's step into the first part. That's the big picture. So, basically, um, Hubble's law is something that our understanding of the universe. Hubble's law has changed a lot about our understanding about universe, and it has been a very fundamental factor to determine a lot about our universe, right? So, simply to put it, now Hubble's law, if I'll explain the diagram later, but for now, if you can check this out, it states that velocity is equal to h naught d, where h naught is the Hubble's constant, and Hubble's constant basically is just a constant that will give us an estimate of the age of the universe, or the Hubble time. So Hubble's constant is a constant put there to understand the relationship between the velocity and the distance. Right. So the Hubble's law, in general, will state that the velocity at which a galaxy moves away from us is directly proportional to the distance. And here, that is, the proportionality is changed by the Hubble's constant. Yeah. So as you can see, this is the formula. Now, this is the core evidence of the Big Bang theory in itself. It means that the space itself of the space and the outer space in itself is expanding pretty much, and it's stretching the red light waves. So here, as you can see, if you check here, we have a little graph of the ranges of the radiations. Now we have red light, which have the longest visible wavelength, right? Now anything beyond that is not visible, so we categorize it as you can see, microwave or infrared, that is below, and ultraviolet, X-rays, etc. So, when it is invisible and when you know it's beyond the red light's wavelength, you name it as, okay, literally, if you put it, it's redder than red, right? Hope that makes sense. It's more red than red, as in it's more redder than the visible red, right? So that is called the redshift of the universe, right? So importantly, the H naught is not just a constant that we use for the equation point of view. The inverse of the H naught will provide the Hubble time. As I've said, it gives an idea about the age of the universe. And this Hubble time has been helpful to understand the estimate of the age of the universe. Now, whenever we say our universe is 13.8 billion years old, it is due to the Hubble time, which is supported by the Hubble constant, that we are able to aggregate this value, right? So if you check here, um, okay, so the universe, okay, when we are trying to get a visible wavelength, or when we are trying to send like receive wavelengths from various edges, or various areas, not edges, areas of the universe, over the time that we have seen that these wavelengths are getting longer, and more than longer, it's going invisible, which proves to us that it has come as long as the red's wavelength, and it is going beyond that, which is making it invisible to view. Now that is where it has gone into the ultraviolet category, or infrared category for that matter. And that is how we have been able to conclude that the universe is continuously expanding. right? So this is how we've tried to categorize it in today's way. So cosmic dark ages, we do not have any light coming from there. Now we have a place where the first stars have formed, and the first galaxy started forming over the time. Now a James Webb telescope is able to look deep into these many light years. Okay. So these many light years, being able to look into these many light years is saying nothing but we are able to look up to those many light years behind us, as in we are able to look into the past. Right. So James Webb telescope has been able to look up to the point where galaxies are forming or the formation of galaxies are seen. Now, Hubble's telescope or Hubble's limit is only categorizing uh, into the modern galaxy formations, and this is these difference from the James Webb telescope's wavelength, the wavelength falling on the James Webb telescope and the wavelength falling on the Hubble's telescope has been considerably variant, as in excuse me, has been considerably variant because from a visible red light, it has come to an invisible, longer wavelength that is beyond red light. So that is where we believe the cosmological redshift has happened, right? So that is about this. Moving on. Yeah. So now, to quantify this expansion or to talk about the scale up to which the expansion has happened, or if there is a cosmic scale factor, that is A here. So, to track this expansion precisely, some cosmologists have used a factor called cosmic scale factor. And the scale factor is nothing but a dimensionless number that will describe the relative size of the universe compared to its size today. Now, one form of looking into it that they have taken is the scale factor today. If we take A is equal to 1, it's the current size of the universe that we have today, right? Now, if A is given as zero point 0.5, then the universe was half its current size. If A is equal to 2, the universe will be double its current size. Right. So this is more technically useful than velocity because it separates the kind of stretching of space from the motion of objects through space. So rather than looking at the speed of an object passing through the space and looking at it, saying how much time has it taken to go around the space, rather than taking the area covered or how much expansion has happened over time through the velocity of motion of objects. This is a more concise way of looking at it in modern cosmology. So before Hubble, the universe was thought to be sort of a very static, and it's not growing, it's not reducing, it's just there. The universe is having a pre-laid structure, is having a size that is already, that is determinable if we had the sources, but it's fixed and static, and it is eternal. It is forever going to remain the same. Now, this is led to another paradox. That paradox we'll be looking into in detail. So, that paradox is called the Olbers paradox, right? So, the Olbers paradox, so sorry. The Olbers paradox is a very interesting paradox that we'll be looking into. Now, Olber's paradox is nothing but Olber was a cosmologist, was an astronomer. So he had a few theories about whether the universe is becoming larger. Expanding is a different thing, but is it infinite or is it finite? So, what do you all think? Like, um, what is the first impression that you all have whether the universe is infinite or finite?
The first impression seems
I,
to be that currently, I mean, the universe is finite but expanding.
Okay, finite but expanding. Yeah, that's a good thought. Okay. But was there a time ever that you thought that universe is unlimited, the sky is the limit, and the universe is just
Yeah,
infinite, it goes on forever?
the
definitely.
thing, yes, the thing is, the first impression is like universe. For now is finite, but the space containing the universe is infinite, which means universe will be infinite. It as
Ah,
it keeps
okay.
expanding.
All right. So you were thinking universe is some sort of what do you say, if you have a little
I mean,
um a plate
yes, ma'am.
and
Yes,
you pour
ma'am.
water into it, the universe
Yes,
is
ma'am.
filling
But
it up.
that's not a correct interpretation. But we can imagine it that way, like a space-time
Yeah.
in some quantum void.
All right. All right. So yeah, okay. So before I explain further, I'll
I,
just
if I
yes,
can
please.
add, I
Yeah,
think
please.
the universe is finite and will
Okay.
be finite no matter how infinitely it expands, because infinity is something, if we refer, is something which is unattainable or unachievable. So
Mhm.
no matter if we are able to quantify something, be it a
Okay.
very big number, it is considered as finite, as it can never reach to the infinite level, as infinity is something which is unmeasurable. So
All right.
I
All
think it can never be infinite. But
Yeah,
yes, what
the thing,
Praful said
but the
was
thing,
kind of
yeah,
the idea that
I know.
the existence of the universe in this time and space bound is what giving it a 3D, or what we interpret it as a
More
existing
dimensions.
universe.
I'm thinking about more dimensions. Like in theory, they say 11
right.
or 12 physical dimensions. And
Hmm,
also
yeah.
there is a concept which is called trans-infinity as it exists. So nobody can say what actually is our universe, where actually is our universe, sorry.
Okay, cool. All right. That is a good realization, because if we try to look at the universe in relation to something that we see, and if we try to put that into a picture, we may not be able to achieve it because that is
One second,
sort
one
of
second.
beyond something we can think of. All these theorems and all these concepts
Mobile number?
will just help you mold your mind to that kind of
Double one?
understanding. All right. Yeah. Before I go into this
My
slide,
number?
just please
Hmm.
give me a moment. I'll just be back.
Hmm.
Yeah.
Hmm.
Please excuse me.
Get copy? आपका ये ना
Yes. Sorry. Okay. We'll continue with Olber's paradox.
और है
It's
क्या
quite an interesting one. So what Olber has done here is now he has tried to conceptualize universe into a level where our telescopes or our resources couldn't reach. Okay. So, apart from his, there are a lot of other observational evidence that universe appears to have started at some catastrophic event that we call as Big Bang, and everything seems to point towards that. But it wasn't always the case, right? Back in the time, people couldn't come up with these kind of thoughts. right? For hundreds of years, like, people always wonder whether or not the universe was infinite or not. And this concept here is actually um, very important in our understanding. Like, there were not a lot of people who followed or showed interest into astrophysics back in the days. So there was a time back in the days when people thought earth was flat, and there was also a time when people thought earth was the center of it all and everything was revolving around the earth. So all these had eventually been rewritten by astronomers. So maybe this understanding that we have right now also may be rewritten in the
So
future.
question,
We
last
don't know, but
number.
this is what we have as of now. And
Hmm.
so,
8
whether or
to
not
9,
there was a
8,
big
9.
bang,
Hmm. Hmm.
there were two big questions that
Last
people
number.
had to, think about. One, is the universe infinite, or did it go on forever? Right. Second, is the universe constant, or is it constantly changing?
Tomorrow will 9,
um,
90.
and that was more harder than the first question to detect, because back then we didn't know the extent of the universe and whether or not galaxies were moving around the universe, and is it expanding there
Out na?
quantity wise. So all of this. So Olber lived in the 18th and 19th century. So um, the resources back then were limited, but he came up with a pretty good thought. Now, if the universe was infinite, then no matter whatever direction you go, okay. So I'll just take this image to explain. Like, let's say you are observing from the Earth, and you have a sphere around you. Okay, we are taking it as a big spherical ball, and whichever direction you look, since we have stars everywhere, whichever direction you look, you may eventually look at a star. And maybe you may be looking at a star that is closer to you, or maybe farther than you. And how did you determine this? Because some stars appear to be more brighter, some stars appear to be less brighter. So your natural conviction is that the brighter star could be closer to you, um, and the less brighter star could be farther than you. And even back then, there were not a lot of beliefs that stars in itself could be of different sizes, because they thought all the stars were of the same kind, of the same size. So it only matters about the distance, right? Closer to you should be brighter, away from you should be not as bright as the closer one to you. They couldn't consider the fact that maybe the closer stars were bright because they were smaller and closer, but there were also some bright stars which were farther than these stars, but extra bright, or more bigger. So those considerations were not there back then. Right. So let's say you're viewing from the surface of the Earth, and there is an entire sky that is filled with stars, and yeah. So to understand this concept, we can take a look at it this way, right? Let's say there we are drawing a sort of a shell of some stars, not some stars, like whatever we are seeing. Like, we are dividing our view into different shells, right? So we are drawing one shell that is, let's say, uh, a billion, or
खेलने लग गई
uh,
अंदर
let's say
बोलो
there
बोलो
is a certain distance in between you, in concentric shells, and some space in between, and let's say that we put these shell in certain distance away. Now we take the first shell, and okay, let's put that from us the first shell is a billion years away, a billion light years away, right? So let's say, okay, R1 is a billion light years away, and there we have the first shell. And let's say the thickness of this shell is maybe 1 light year, right? And then we have a second shell, another billion light years away, equidistant. And now that's 2 billion light years away from your observation, right? In such a way that the second shell is twice as far away from you as it is from the first shell. Now, the thickness is 1 light year, and we couldn't. We would count the number of stars that would appear in one of those shells, sort of a billion light years away. Now, look at the second shell. We have that is around 2 billion light years away from us. And how many stars would be in that second shell? We take the square, right? So basically, we can say that the of these volume of containing in these shells could be v is equal to 4 pi r square into the thickness of the shell, and the thickness of the shell is as equal to 1 light year away, right? So when we just put the delta v, or volume, is equal to 4 pi r square into delta r, that is the difference here. This difference you see is delta r. Okay, and that same delta r is being repeated for every shell. It's the same thickness, 1 light year away, right? So we have tried to repeat this over a few shells. We have tried to keep as shell 1 will have delta v1 equals 4 pi r 1 square into delta r. Shell 2 similarly, shell 3 similarly. Right. So so in this case, if we were to count how many stars would be in these each shell, then we would have to deal with proportionality of how much volume is contained within these two shells. So one would be the volume of the first shell, and delta V2 will be the volume of the second shell. And in like, let's say we draw another shell, we'll have a third shell as well. So the third shell, naturally, it's equidistant. So you can assume that it is 3 billion light years away from you. And again, the shell thickness is 1 light year. Right. So so in this case, how would you find the volume? Well, the volume would be equal to the surface area, as we've just established, and it's kind of like a ball that you're standing from. So it is like a sphere, and the surface area, that is why we consider as 4 pi r square. And the thickness, as we know, is delta r. So the volume of the shell will be 4 pi r square into delta r. And for the first shell, as established here, and second and third shell also, as established here, one thing we have to be considerate here about is R1, R2, and R3. That is, subsequently, the R1 is 1 billion light years, and 2 billion light years, and 3 billion light years, respectively. Now, since the volume is proportional to the distance squared, as we can understand from here, all the constants cut off, you can understand that the volume is proportional to the distance squared. Um, this proportionality would mean that there would be around 4 times as many stars in the second shell as compared to the first shell, because there is an r squared coming up. So if, let's say, here there are like a specific number of stars, that is x number of stars. So now when it is squared, we'll have around 4 times as many stars in the second shell. Similarly, we'll have that again squared, we'll have 9 times as many stars in the third shell. Right. As it gets far away, it keeps increasing as we square it out. Right. So in this case, uh, since we have a thickness of 1 light year 3 times far away from us on the third shell, we could have, or like, let's say not 3 times, we take n number of times. Let's say we take like 5, then it could get squared of a squared of a squared. Again, it keeps going, right? So what happens if the star is farther with the light? What will happen with the light, or how the light would vary as the star is going farther from us? What would be
More dimmer.
more dimmer, right? That is the assumption we have, like something, a light source kept right in front of us and a light source that is far away could have a brightness difference when it falls on our eyes, right? Now, the farther the star, obviously, as our understanding goes, the dimmer the light will become. And we understood at the time from that the intensity, if you come back here and check, that the intensity or the amount of light you would get from a light source, or in this case, a star, would be indirectly proportional to the distance squared. So we can say I for intensity is directly proportional to 1 by r square, right? So if a star is twice as far away from us, the intensity should probably be the quarter, or 1/4, or 1 by 4th of what we see or what our eyes can perceive, right? But in that case, it could be 4 times away from us, but we are seeing only quarter of it because of the intensity being reduced or dimmed by the distance, right? Now, that would be 4 times, and this will give us a sort of impression wherein the light you would get from the sort of region of stars would be exactly the same as light you get from this region of stars, right? So, I'm sorry if there's a delay. Okay, yeah. So, what I mean to say here is, if the intensity is 1/4 as it goes farther from us, right? And the dimness is being masked by the fact that there would be 4 times as many stars, which
हमारी डाकছে
sorry, is someone trying to speak?
No, I think her mic got accidentally turned on.
Okay, no problem. All right. So, what I mean to say is, let's say, um, I'm having 3 light bulbs in front of me. Okay. Now I'm squaring it at a distance, maybe 3 meters away from me. I have 9 light bulbs there. Okay. Another 3 meters, I have the square of that many light bulbs. Okay. Another 81 light bulbs there. Now, if that's the case, do you think the light from each of these shells will be dimmer?
No,
If we look at it
since
individually, like individual stars, it should be dimmer. But as a whole, we will be experiencing the same amount of luminosity, so to say.
Exactly. So we are not looking at an individual situation here. We're just trying to get the collective amount of intensity that will fall onto our eyes,
খিদে পেলে
Yes.
খেয়ে
right?
নেবে এবার
Yeah. So,
সব পারলে খেয়ে
in
নেবে
that case,
ঠিক আছে
as I've said, I'll just repeat it again in case if someone hasn't
আরে তুমি
gotten yet.
মনে হচ্ছে এক করবে
I
দুটো
have
আলু
three
রেখে
light
দেবে
bulbs in
খেয়ে
front of
নেবে
me, and the light is falling onto my eyes. Maybe let's say
না এবার পুরোটা যদি তুমি না খাও সেখানে আমি কি বলতে পারি
half,
বলো আমি যে
maybe
তোমাকে
1/4 a kilometer
বললাম
away from
এবার
me,
তুমি যদি মনে
like
মনে
250
অন্য
meters
কিছু
away
ভেবে
from me,
খাবার রেখে দাও
I have
সেখানে আমি কি
9 light
বলতে পারি
bulbs.
বলো
Okay. And another 250 meters away from that, you have 81 light bulbs. This is just being squared over and
না
over
তোমার
again,
আমি কি
right? So,
এবার তুমি
would I be getting the exact same light that
খিদে
I'm
পেলে
getting from the 3 light bulbs that is just 250
বললাম খিদে
meters
পেলে
away
খেয়ে
from me,
নেবে
the same as the ones I'll be getting from 750 meters away from me?
না আমি সেটার জন্য না ভাত আছে
We have
ভাতও
just
রেখেছি
established
তরকারিও
that
রেখেছি
we will be getting the exact same intensity because as the distance is increasing, the intensity has to naturally decrease. But this is being compensated by the amount of light sources.
কাজ
As in,
মোটামুটি
near me,
দেরি করে
the
এ
bright
করে হবে
intensity that I'm getting onto
দু
my
তিন মাস
eyes
হয়তো
is
পরে
maybe just 2, 3 stars.
मैं तो शुरू बोल
But
रहा
as the distance is growing, where the intensity has to reduce individually, we are having in place of 2 3 stars, I'm having around nine and above stars. So due to the since we are taking the stars as a collection, now
And
that combined, yes, please.
ma'am, but also due to
এই না অল্প
distance,
করে শুরু
shouldn't
করলেই
the
পারে
light,
আর
I
মনে
mean,
হলে
wouldn't the
অল্প
wavelength of
একটু
light will
তরকারি রাখবে
decay
ভাত
and it
রাখবে না
will fall out of
আমি
the
ওই অল্প
visible light
তরকারি দিয়ে
zone?
Yes, ma'am, I had the same question.
Now wavelength will
আর কি বলবো বলো
reduce when there is a refraction happening. Okay, so in most of the cases, we are most of the theories or most of the concepts that we have a theoretical knowledge about, we conveniently try to neglect
মানে
or
আরেকটা
make the
তোমাকে বলতে পারি
atmospheric ways of affecting negligible,
তুমি
right? So we are taking in an ideal atmosphere or an ideal
সিএমএম এর এটা
environment.
আমি আইডি দিচ্ছি
Let's say there is no scattering of
তুমি কি
light
অ্যাডমিশন
happening
নিয়ে নাও
and the wavelength is
অ্যাডমিশন
not
নিয়ে
decaying.
একা একা করে নাও আমি তো এটাতে
Okay,
হয়ে ফেলেছি এখন
now this is just theoretical, this is just a concept that is put out. Any sort of derivation you take or any sort of
আচ্ছা বাড়ির ভাই
theoretical
এই
concepts that
পরে
you
যাও
take, there will always be some assumptions wherein we assume certain factors are negligible, so we take whatever is left out and then you arrive
ওসব
at a conclusion,
এমনি দেখছো
and then
দেখো
in the conclusion
কি
is
হয়
where we
সেটাই
add the external factors and see how it turns out, right? So let's
হুম
say
সে
in
তুমি
this case
করবে
we have
এরকম সিএমএম যদি করো
so
তোমার হার্ডলি এক
don't
মাস
look at it
এক
as a
মাসও
one
লাগবে না করে
dimensional thing. Think of it as we are living inside a sphere, right? A spherical ball. So all around us we see one shell that we are covered in, one transparent shell, and that transparent shell
হুম
has x number of stars,
হুম
and there is an outer shell. Since this shell is
অনলাইনে ফরম্যাট
transparent,
আছে
there is an outer shell with 4 times as number of
কপি করে
stars
নিজের নাম
as the
বসতে গেলে
x number of stars we had on the
কত
first shell. So that is
পেয়ে যাবে
obviously
আমি বললাম যে
dense with
জোগাড় করে দেবো
brightness, right? So whatever light is falling on us from the shell closest to us,
বুঝলি
there is less number of stars, but there is enough brightness because it's closer to us. The shell outside that
ফার্স্টে সিএমএম
is
করবে ভাবছো
obviously the intensity of the individual
যদি
stars are less, and there is a shell, and there could be a lot of
যদি
decaying
মনে হয়
happening,
আরে
but we are ignoring or neglecting the factors like any
আরে
atmospheric
গুগলে মারবে
conditions or particles out there,
গুগলে
etc.,
মেরে
right? In the
ফোন
outer
নাম্বার
space,
পাবে
if you
ধরাধর ফোন
simply
করবে
take the outer space, there are a lot of
ঠিক
other
আছে তুই
particles
ওকে
like
খাতায়
dust
লিখবি
particles, gas particles, all these can scatter light, right?
খাতায়
So
লিখে
we are
যেটা বেটার
conveniently
মনে
just
হচ্ছে ওখানে
keeping them away
চলে
just
যাবে
for the sake of this theory,
বেটার এবং
right?
ক্লোজ
Okay.
ঠিক আছে
So the outer shell, the second shell that you have around you is
নাহলে
giving you almost the same intensity
সামান্য
because
জিনিস
it is farther away, as
একটা
in the
ইউপিতে
distance
আছে
has
কিন্তু
increased,
অতদূর তুমি যাবে না
but
তো
the
বলছি
population of stars in that shell is 4 times as that of
এখন ক্লাস
the
চলছে
one
না হলে
closer
আমি
to you.
ইউটিউবে
Now,
একটা
again, let's imagine
ইয়ে আছে
another shell is
ও
there
দেখায় মাঝে
beyond
মধ্যে
that,
ওর
and that
সঙ্গে
has
যোগাযোগ
nine
করতে পারো
times as stars that
মারো না
is
ইউটিউবে
compared to
যখন ফ্রি
the
টাইম
shell
পাবে
near you.
ইউটিউবে ডাইরেক্ট মারবে
So, even though the
দেখবে
distance
সিএমএম
is
সম্বন্ধে দিয়ে দেবে
decreasing the intensity,
দেখবে
the
ওরা অনেক সময়
population
কন্ট্যাক্ট নাম্বার
is
ছাড়ে
increasing the intensity.
তলায়
Does that make sense?
হ্যাঁ
It
ওইভাবে
is just
কন্ট্যাক্ট করতে
balancing it
পারো
out each other.
আর
Now, if
ডাইরেক্ট
this
গুগলে
was
মেরেও
true,
কন্ট্যাক্ট করতে
right?
পারো
If this had continued to be
আছে
true,
অনেকেই কেরিয়ার আছে
okay, then we have
ইন্টারেস্টটা হচ্ছে
a
ব্যাপার
lot of shells going one after the other. I've just taken for the
টাকা
convenience 3
টাকাটা
shells
ব্যাপার
here.
না টাকা তো
Let's say it's an infinite universe. We have shells after shells after shells. We have
ইন্টারেস্টটা
shell 1, shell 2, shell 3, shell dot 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 shell n, right? Now, if there are
টাকা তো
infinite number of shells out there, what do you think
মিনিটে মিনিটে করেও
the
টাকা
sky
রোজগার
will
হয়ে যায়
look like?
Full of stars if we are neglecting
Interesting.
the distance.
Stars, okay. We usually tend to see stars during night, right?
I mean, like night won't exist. We will get
Exactly.
we will get
Yes.
light from another star if sun is unavailable.
মানে তোমার ইন্টারনেট কোথায়
Exactly. So then we don't have a dark
ব্যবসা
sky
করলে
at
ব্যবসা
all. Our nights will look as bright as the day. You agree with that?
Yes, ma'am.
Yeah. Now, is that happening?
Nope. No.
Exactly. Now, that is how Olber has proved that we do not have an infinite universe. We have a finite universe wherein we have few shells up to which it goes, and only the stars that's coming from these many shells are there. If there were
বাড়তি অসুবিধা
infinite shells, then we wouldn't be having nights at all. So this was the conclusion of the Olber's paradox.
I have a doubt over here.
Yes,
বাড়িতে
please.
হবে না
So, shouldn't we take into account the speed of light in this case? Because let's say there's a
বাইরে
star
এখান
at the
থেকে
edge of
বাইরে
the
থেকে
universe,
কিছু চেষ্টা করতে পারো
Okay.
but its light hasn't reached yet
বাইরে তো ডিপ্লোমা
to us. Let's say there are a lot of stars whose light hasn't reached us. So,
হ্যাঁ
wouldn't that part of the universe, that part of the sky for us be
হ্যাঁ
darker?
Okay, so if I'm not wrong, I think you mean
ওদের
there
মধ্যে
could be
বোঝাপড়া
infinite number of shells according to this paradox, but it's just as the distance is increasing, maybe it's taking time for the light years to reach your eyes.
Yes, and once it
ও
reaches
হয়তো
after
1%
billions of
হয়
years and
2%
all,
হয় বেশিরভাগ হয়
some
না এরকম
stars may die,
Hmm.
right? I mean, they must have
আমার
been
তো
dead
চোখে পড়লো না
at
তবে
the
আমি
current
লোকের
time, but
মুখে
after
শুনেছি যে
billions of, after say
হেল্প
2 or
করলে
3
অনেক
billions
কিছু
of
হয়ে
years,
যায়
we are able to see the effect
বাট
by seeing that the sky has become darker now. The
Right.
star does not exist. The star doesn't exist
মেয়েদের
right now,
এরকম
but
পাওয়া যায়
we
না
will see that after, let's say, 1 or 2
একটা
billion years.
একটা
Right now there is light,
Absolutely.
but after that there won't be.
আমি বললাম,
Exactly. Exactly. That
আমি
is
কন্ট্যাক্ট
also one what do
কন্ট্যাক্ট
you
করলাম
say,
বলে
one contradiction there also. If you have thought
আমি একটা
about
মেয়ের
this,
সঙ্গে
one another
কন্ট্যাক্ট করলাম
contradiction
তো
is uh, we
তোমরা
could be
কোনো
having
রিপ্লাই করো না
apparent
আবার
views
ফোনে
as
সুইচ
well.
অফ করে দিয়েছে তাহলে
There
কল
could
না
be
করতে
one
পারি
star that is giving us two sources of light just because of apparent viewship,
মানে
right?
আমার
Even those kind of theories are contradicting this, right? So all those are contradictory
আবার
theorems that is trying to oppose this paradox. But the solid part here is, since we are able to see a darkness where,
লাস্টে মানে
okay,
কি
if
করলে মানে
let's say
ফোন
a
করছি তো
far
ফোনে
away
ঢুকছি
star wherein the light
রিফ্রেশ
is
করলে
not
দেবো না
has not reached us yet, okay, and that
হ্যাঁ,
star
বুঝতে
is
পারলাম
so far away that we could be receiving the light that is emerging from this star maybe another million years later, then there is there is a light year
আপাতত
difference from
থাকো
there,
চেষ্টা
but at the
নিজের চেষ্টা
same
যেটুকু
time
হয় ওইটুকুই
what
করো
we consider is this star is
দিয়ে
there and the light
আপাতত
is reaching us in, what do you say, a few light years. And if this is prolonged investigation, like a prolonged what do you say, prolonged experiment that is done, then in that case, how much of these stars, like you just don't have one star somewhere out there that is
কোনটা
having the delay in light, right? So in an outer shell or in a certain distance, the population of stars could be immense, and there could be stars in between these shells. So we have tried to take more like an integration here,
Yes.
wherein we have taken only a strip of it, like, we have taken like shells as in the strips of here of the entire sky, and we are trying to find the intensity, how the relation of the intensity is in general, So there could be a lot of stars in between that which could reach us faster, and this population could be much more than what is on the shells, right?
Yeah.
So all of
So,
those are there. But hello,
yeah, I'm listening.
I'm sorry, I didn't get you. Can you repeat?
I'm listening. I'm listening.
Yeah, yeah, okay. All right. So, this is more like an integrative, what do you say? We are taking a strip to just, get the concept right. And this paradox, that is why in itself it's called a paradox, because there is a belief on this as well as there are a lot of contradictory on this. Now, all those paradox have given the closest to closest proof or evidence as to the universe is not infinite, right?
Yeah.
So
And one more thing I would like to just discuss in this, it also seems intuitive
okay,
that the age of the star
sorry,
will,
come again.
the age of the star, the
Okay.
time the star exists,
Mm.
is in, I mean, it's intuitive that it should be greater than the time its light is taking to reach us.
Exactly, yes.
Yeah.
Yeah.
Yeah. So this
It's
will support this, Olbers. I
sorry.
mean, so this intuition will support that the sky should look bright.
The sky should look what?
The sky should look bright all the time. This intuition should support that.
Support it, yes, absolutely. Now all these intuitions, all these contradictory things are all considered, and the paradox in itself is just trying to state that in case if there were strips of stars population that was taken, and there is, like, if so, imagine this is back in the 18th and 19th century. So all we could imagine at that point where, in, what do you say, in real time, whatever we see, we try to conceptualize it like that. Okay. So we just have a knowledge of what we see, and we conceptualize around whatever we are seeing, however we are seeing, right? So he has just created a sort of uh, a thing where he knows infinitely, to a point there could be, I mean, finitely to a point there could be humongous population of stars wherein you take strips of it, and these strips are arranged. Do you think a strip of stars could be taken that way, wherein you can equidistantly arrange that these many stars are there, and the next strip should have four times more stars, because stars are constantly moving, they are changing places, they are not stagnant. So all these are just, what do you say, these are not very realistic when it comes to, when if you try to look out into this the through the telescope, and one day if we are able to get the adequate resources to look beyond what we can predict, these are not going to stand valid. But this is the closest evidence that we have that states that the universe is finite. Yeah. So lot of controversies have come here. Lot of it's a paradox theorem in itself. So there are a lot of people opposing this. There are a lot of studies opposing this. Uh, but we have been able to base most of our concepts in the outer space based on Olber's paradox as well. And at the end of this assumption of this paradox, a lot of other concepts have been, we are now in the age where a lot of other concepts we have the resources to prove. So we have proved some of those, like the expansion of the universe, that has also been proved through certain wavelength differences. Now that, or the cosmic scale factor, all of these have been proved, uh, and the Olber's paradox played a major role there.
I have one more point over here. So if we
Yes, yes, please.
assume that this Olbers paradox proves that the universe is finite, or this
Yeah.
theory proves, so in a sense, we can say that we might be the dark places in the sky might be the edge of the universe itself.
You mean like a dark age sort of area?
Yeah, in when we look in the sky, the black part of the
Mm.
sky, the part
Yeah.
that's not the stars. So that part, according to this, should be might be. I mean, they could if we zoom them, they could we could see more stars. But eventually, the dark part of the sky can be the edge of the universe, right? Because there's nothing in between. Because there are no stars in between, something like that.
No, Nimit, I would like to correct you over there because there are millions of stars in the night sky that you can see right now. Now, most of them are not visible or looks dark because of the atmospheric
Oh,
contaminants,
okay.
right? There are a lot of layers of clouds that it has to overcome to be visible for the light to pass. And there are some apparent shifts in the star's positions that when we see from the earth. So actually, more than what we see on the sky on a normal night, that's, I would say, not even one part of a million of what's actually there.
So I similar related to this concept I read somewhere. So I
Hmm.
mean you're saying if we keep on zooming a square, so it
Okay.
will be filled with stars all the time. So according to
Mhm.
that, if in a sense if the speed of the light were to be infinite, even then the night sky would have been bright.
S- Speed of the light to be infinite?
Yeah, I mean in a sense the hypothetical situation I mean to say if if the light of the star were to reach us at the same instant,
Oh, okay.
in
Cool.
that case, I mean, neglecting any other physical effects it was affecting, any other physical
Oh,
situations. So, in
got
that
it.
case, the sky, I mean, the projection of all the stars, let's say, projection of all the stars in the universe, if they were to fall on a sphere over the earth at the same time, the sky would be
Then
bright.
we probably wouldn't have a night.
Yeah, yeah, correct, correct, correct.
Yeah.
Yeah, got it.
So that is if you ignore all the all the atmospheric factors and everything. Yes, I don't believe that we wouldn't have a night. We could have a what do you say? We could have a very bright night.
Yeah, kind of like a noise that we see on the TV, the black and white noise, something like.
Exactly, like more like the glitch part of it, right?
The dark spots will be less. Like we see the white.
Dark spots will be less. Yes.
Correct.
Now all these, uh, it could be like that, and plus it could constantly, if the light can reach us in real time, then probably you can probably see stars dying. You can see the formation of stars immediately.
Correct.
So wherever the light goes off some places, you can immediately see somewhere else a new light coming up. So if it reaches in real time, then I think that's beyond imagination, at least for me.
Definitely.
Yeah. So yeah, it would look more like the glitch you see on the TV. Yeah. Some places it can, flicker dark. Some places it can flicker a little bit. And okay, so in that case, if there are no atmospheric contaminants out there, then you wouldn't be seeing a lot of wavelengths or colors also. Could just be like some, white light here and there. So you wouldn't be seeing colors, as in you wouldn't be seeing it yellow or red or blue or anything, probably, because the wavelengths are happening because of the contaminants,
Yeah. Yes.
right?
But the wavelength is also
Got it.
happening because of redshift, also, right?
Yes, absolutely.
Yeah.
Yeah. That is again factorized based on scattering of light.
Correct. Correct. Yeah.
Yeah. So the scattering of light to be taking place, it has to have some medium where there's a diffraction happening. Yeah. Okay. So that was about Olber's paradox. Great discussion. Okay. So we have We have another 3 more slides. Would you all be able to wait? We're already beyond the time. Anyway, meanwhile, I'll probably just take a small screenshot, customary screenshot. Give me a moment. Yep. Oh my God, the weather is very bad where I'm living right now. Is anyone in Bangalore right now?
Delhi.
Ah, okay, cool.
Same here, man. Greater Noida, Delhi.
Sorry, come again, Praful?
Same Greater Noida, Delhi. I was saying
Ah,
like,
okay. All right, all right. No, Bangalore is not a great place to be at this particular time.
You mean the pollution?
monsoon is like just
Retrieving monsoon.
Yeah. I think Delhi could be facing a lot more pollution in it.
no. I think so. Main part of Delhi, not like the
Ah,
remote area, Noida area. Whatever. But the
all
cold
right.
is like just entering.
Yeah, people are getting sick over here too. I'm sick too.
Ah, okay.
Everyone is.
All
I was
right.
sick 2 days ago
Oh,
because
okay. Hope you're doing well right now.
yes, man.
Yeah. Okay. So, okay then, we'll then sit for another 10-15 minutes if that's okay.
Okay,
Yes,
ma'am.
sure.
Yeah.
And you
Okay.
have to give us tasks also.
Yep. Good call. Yes, I have to give you tasks as well. Right,
So,
right. Yeah.
can you
Three
just
more slides. Sorry,
can,
come again.
can you give the slides as a part of tasks too? I mean, it will save the 15-20 minutes.
Oh, so the task slides are not entirely related to what I'm going to discuss right now.
Okay.
Uh, it is partially though, but then it might be confusing as to because I'm combining a lot of contents to give you that one task.
Okay. Okay. Got it.
Yeah. Oh, we'll wind it up pretty soon. Yeah.
Yeah.
Okay, so the next one we are going to be discussing about CMB or the cosmic microwave background, and we'll be moving into the inflation theory for the next slide. Uh, yeah, so CMB is basically more like an EM radiation, electromagnetic radiation that is left over from the very early universe. Okay, so it is called the afterglow or the baby picture. That is the technical name for it. It's the afterglow or baby picture of the universe or the cosmos. Now, with that regard, we are moving into our first part of the universe's baby picture called the recombination era. Right. So the recombination era is basically when the universe became transparent. The story of the CMB begins around approximately 380,000 years after the Big Bang, right? And that is during the recombination era. So that is believed to be during the recombination era. Now, what happened before recombination? So before recombination, the universe was so hot that was told to be around 3,000 kelvins, and that the matter existed as in the form of an opaque, extremely superheated plasma, and uh, this superheated plasma had a lot of free electrons um, and had an atomic nuclei with mostly protons and yeah, so that was the existence back then because of the enormous temperature, and the photons, or as we call it, the light particles, could not travel far beyond or far before the scattering of some free electrons here and there. Now, this means that the universe was extremely electrically charged. At the same time, it was pretty opaque, as in it was pretty opaque. Couldn't see through anything. It was opaque. The atmosphere was opaque, and it was like a very dense fog that it couldn't really send out light or get in light into it. It could just highly scatter whatever light particles were going through it, and plus it was highly electrically charged. Now the event was that as the universe expanded, it started to be more cooler, because obviously it started expanding, and the heated particles were just moving more freely rather than tightly packed. And this moving freely, or this expansion, has caused the universe to be more cooled. And when the temperature dropped like below 3000 kelvins that it was previously, the electrons finally slowed down. And this slowing down caused it to be captured by the nuclei. So the nuclei now, after the capturing, has both electrons and protons. Earlier, it was mostly just protons. Now, this nuclei capturing the electrons along with the already existed protons made it more stable neutral atom. Now it's primarily hydrogen and helium. Now, after the event came the release. Okay. So, in this release, basically, the moment the free electrons disappeared from the other parts, and not from the nuclei, but the other parts of the universe, the photons were no longer constantly scattered, and they were suddenly released in such a way that it could freely travel through the space. And that freely being able to travel of the photons, that is what we see today as the light, or as the cosmic microwave background that we see today. So hope that much is understood. So I've just told you what happened in the beginning, and then how the recombination era happened, and what happened after the recombination era. Hope it's clear till here.
Yes, ma'am.
Okay. Now, we are quickly looking at something called a black body spectrum. So you had all done a spectral line emission analysis of the SS Cygni, I think the contradictory star. Uh,
Yes, ma'am.
yeah. So now we'll be quickly looking into what black body spectrum is. Now, as the universe continued to expand, right, after the recombination era, as the universe continued to expand for over the next 13.8 billion years, as we all know it, the wavelength of these released protons, that the protons were now more scattered and the light could reach everywhere. So the wavelengths of these photons were stretched due to, can someone tell me why it was stretched?
Because the universe is expanding.
Uh,
Now the universe is expanding because,
Ma'am, I didn't get the question.
okay, so I told you the photons were less scattered, I mean, more scattered now, so that the light could reach everywhere, right?
Yes.
So over the time, the light could reach everywhere, and the wavelengths of these protons started increasing or stretching. Now, this was because obviously the expansion of the universe. Now, that the base reason for all of this is
Dark matter.
no.
The energy which it
I
held.
mean, the dense energy was expanding in an infinite space. So, like, light is a type of energy, and it was expanding, so it's get diluted, and diluted means wavelength gets increased, something like that.
Not entirely, no. I've given two clues in the question that I just asked itself. There is a wavelength involved, and there is expansion of universe involved. What could it be? I'll go for it. So that is solely because of, guess what? The cosmological redshift.
Mm.
Yeah. So the wavelengths of the released photons were stretched, and stretched in such a way that the wavelengths were growing longer than the red wavelengths, but invisible to a point, maybe. And that invisibility has caused some sort of affirmation that there is a cosmological redshift happening. And in turn, we concluded that, okay, there's definitely expansion of universe that's happening, right? So because of these, that we could have more light out into the, I mean, as in the scattered photons could have a bigger wavelength, right? So this stretching of the photons caused the energy of the radiation to drop dramatically. Um, and this in turn started giving out the radiations which are cooler. From around 3000 Kelvin, it came down to its current extremely cold temperature, which is um, like sort of minus 2.725 Kelvin. I think I missed the minus here. But it's that is the lowest temperature we have out in the outer space. So minus 2.725 Kelvin. And the CMB, or the cosmic microwave background, sort of possesses also a perfect black body spectrum, right? Now, black body is always considered to be a thermal, something related to thermal sort of absorption criteria or sort. So here, black body spectrum is again sort of a perfect thermal emitter. Now, this black body spectrum has become one of the most precise spectrums ever measured in the nature. Now, this spectrum is a very strong confirmation once again of the Big Bang model, and that in turn has predicted that there has to be some thermal radiation that has to be existing.
এখন নয় 12টায় যাবো
So it has all come down to the point where there was a very hardcore thermal radiation that probably scattered out a lot of particles and caused it to expand, which again points down to the good old Big Bang theory. Hope this much you've got.
Yes, ma'am.
All right. So moving on, I am giving a very small account of anisotropies. So CMB anisotropies is um, can someone tell me what you know about anisotropy from chemistry? What sort of structure is anisotropic structure?
When same chemical formula can be in can exist in different structures, but the composition or the number of um,
So,
elements is same.
Okay, number of elements
um,
in different formulas.
Not
I
formulas,
mean,
but the structure of the
Oh,
combination
okay,
is different.
that's right. Yeah. Okay. Okay. Does anyone
just
else want to add? I think someone else was talking.
Same element but with different number of neutrons.
Different number of
mm,
neutrons.
I,
Okay.
I mean, uh, I mean, the physical property change just based on orientation.
Yeah. So basically, it all talks about a variation in orientation, right? Of the same element when there is a difference in orientation. Okay. So that is exactly what is happening here. CMB is the exact same element. The element here is the universe. And when it is having a different orientation when it comes to the structure of the universe. Right. So the seeds of the structure that we see here can be accounted as like the CMB while the CMB temperature is sort of uniform to an incredible degree, there were a few space missions like WMAP,
Can you?
and we had Planck and all these
अरे
space
नहीं लिखा
missions. So it started right from 1965. It was Penzler's and Wilson. So Penzler's and Wilson, it
अच्छा मैं दिए थे
sort
और
of
ये नंबर की
detected the temperature fluctuations of um, the universe like this, when it could go around and capture whatever they got, right? Not to a farther point, but they were able to detect some tiny temperature fluctuations or anisotropies, and they could do only about one part of the 100,000 that it is completely. So it was one over 100,000, that only that fraction they could cover and get a temperature fluctuation there. And these minute variations are extremely critical because they represent the sort of the slightly denser means cooler spots, right? And slightly less denser, now less density is happening because it is more like a warmer spot or a hotter spot. Now these regions in the matter, um, in the matter distributions of the early universe, etc. Now these tiny density differences were giving us or becoming the initial seeds of the gravitational instability that we could later observe, right? So over a billions of years, or over so many billions of years, gravity has amplified a lot more in the denser region, and causing the matter to clump together, and these clumping together has formed the first stars, and then the first galaxies, and eventually the large scale structures have been formed in the cosmic web. Now when these satellite missions, like we have Kobe in 1992, and WMAP in 2003, and we have Planck below, yeah, Planck in 2013. So all these, they found that it was almost perfectly uniform, but tiny variations were there, and that again we call is anisotropies. And these has brought up to the final sort of temperature mapping that we have of our universe, right? So different space missions have given different values because of how the denser and non-denser areas have instituted gravitation throughout its content. Now gravitation has been more predominant in the denser regions, and this is the final, as of 2013, this is the temperature mapping we have of the universe. So this is the anisotropies and how the temperature mapping or the cosmic microwave background we have. Excuse me. Moving on, we have something called an inflation, right? The inflation theory. Now I've just taken this universe as a picture here. And what I'm trying to say is, let's imagine this picture is the front view. Okay. And whatever, let's say, we are adding, we are trying to look at it from a side, and that side view, but that side view, this probably looks like a flat surface, or more like a, what do you say, a world map sort of image, right? But if you look at it sideways, we see that there is a lot of development into widening the horizons, right? Now solving the CMB's problem that we saw in the earlier slide is what the inflation theory does. Now, the CMB represents some very compelling evidence for the Big Bang to have taken place. Um, but the problem is the very existence and uniformity of the CMB has introduced some extremely profound paradoxes that we have today. Now, these paradoxes are not being able to be explained by the standard models without the use of the inflation theory. Okay. And in the inflation theory, we are going to be discussing first the horizon problem. Okay. Now, the horizon problem is by far the most important one. So, if you see here, I'll just zoom into this because these points are what I'm going to discuss. So, here for the horizon problem, the most famous CMB or the microwave background, cosmic microwave background paradox is the horizon problem. And when it comes to that, some regions of the CMB on opposite sides of the sky, like for example here, opposite sides of the sky appear to have the exact same temperature, right?
बोलो
So it could have around plus 2.725 kelvins, etc.
आज के
Now the paradox here is that
अच्छा
given the age of the universe, as we know it, it's 13.8 billion years, these two distant regions, as in two extreme ends of the universe, are extremely far away um, for the light or any sort of casual influence to have traveled between them that far in just 13.8 billion years, because the light years in itself would take more than that. And within this time, for extreme ends of a universe to experience similar temperatures and for the light to have traveled that fast to both the extents, that is extremely impossible, right? So, in other words, we can say that they were never in casual contact after the Big Bang to exchange such huge amounts of heat and reach in a sort of thermal equilibrium between them. But yet, they are perfect thermal equilibrium. How? Can someone tell me how?
Ma'am, can you repeat the question?
Yeah, so I'm telling you, in the beginning, when we had the CMB plots that were plotted, okay, years ago, when there was CMB plotted thermal mapping, we found that the extreme ends of the mapping had almost the exact same temperature. Now, for this to happen, the heat or the radiation or light should travel from one end to the other within these 13.8 billion years, light years. But we know our universe is extremely huge, and light to be traveling back when we checked these thermal or temperature mapping, to for the light to be traveling across the ends of both these, supposedly universe back then, uh, that was impossible for any sort of heat or radiation or light or any sort of casual interferences to be happening across the ends of the universe. That was impossible, but still they were observed to be in perfect thermal equilibrium. Can you tell me how?
I mean, can't we see the CMB in such a way like it's originated from center and like expanded in a spherical way, equal from all sides, not like in a linear way, like in the second picture as we are seeing. It can just be
Yeah,
said
but
as an interpretation.
I understand. But in that case, your other diametrically opposite sides also should have the exact same temperature. If it is coming from the center in an equal way, equal distribution all throughout, then your even the shorter ends all over the boundary should have
Also,
equal distribution of temperature. But here the concern was the extreme ends, as in the longest side of this had the exact same temperatures. How?
so can't we just take it as a coincidence? Like, for example, if we see in the front there is a great void where it is very cold. I mean, matter is almost negligibly present where, yeah. So can't we just take it as a coincidence, like a chance of luck that it was in thermal equilibrium while other points were not?
Yeah. Now, the problem with science believers is that they don't believe in coincidences. So now, when it comes to astronomers or scientists and all of them, they don't believe in coincidences. They need to have a scientific explanation to everything that's happening out there.
Ma'am,
So, Earth became habitable and life started forming is not a coincidence, according to them. It is because there was natural selection and there was an adaptability wherein single-celled organism could had the enough appropriate environment where it could develop into multi-cell organisms. So all these are scientific explanations. Well, it may or may not be what they're saying, but coincidence is not something you can, you know, tag a phenomenon in astrophysics or
Ma'am,
cosmology.
probability. Ma'am,
Sorry?
probability using maths. Probability using maths.
Hmm. Okay, the probability of what?
I mean, existing that some fundamental points are, I mean, I'm just saying it as a theory, not
Got it. Yeah.
absolute concept.
Okay.
The chance of, like I'm saying that these 2 points are in thermal equilibrium. We
Hmm.
can't we just like say it, result of probability or something like chaos theory, the branch of physics which derives order from chaos.
Right. Okay. So that is one way to put it, wherein you have a probability in everything, and there's always a chance of something happening. And yeah, of course. Now, the scientific explanation given to this inflation theory or the
can
solution to
I
this is
can I try? I mean, before you when I give a disclaimer to this, and if
okay.
I want to just keep my idea ahead, I was thinking that maybe not from the center, but it started from a point. Because if it starts from a point and then
Hmm.
you extend two lines parallel to the point
Hmm.
with the same rate, so both the lines will, no matter how long you stretch it, the angle will be the same, and the length will automatically will always be the same, just like a protector.
Exactly. Damn, dude, you've spoiled a lot of content for me. Anyway, so yes, that's exactly what's happening here. So what I mean to say is, back when something of this sort happened, our universe could have been around a 400 million light years of size, and then at that 400 million light years, it could reach across. And then what happens from that point? It started expanding. Okay, from that point it had a quicker expansion over time, and that expansion has evenly, gone across, and it has reached to the 13.8 billion years now, with almost the same thermal or temperature across. So this is the proof that the inflation theory or the expansion of Big Bang, expansion of universe, sorry, expansion of universe is happening. Now it's said that um, some theories about it proposes that a period of extremely rapid exponential expansion has happened. Okay, and this happened in like the first tiny fraction of a second. Like in a tiny fraction of second, there was an expansion of around um I've added it here, 10 raised to the power of minus 36 to 10 raised to the power of minus 32. That those in those many seconds there has been an inflation happening. So it was happening very rapidly and exponentially, is what some theories about inflation states, right? Now the mechanism will state that before an inflation began, the entire observable universe was confined to somewhat an unimaginably uniform region, right? So it could have been like to a very small size. The whole thing could have been in a very small size, where it started, and the Big Bang happened. It created a sort of a small size, and then from that point it started inflating, and and it
Anyone?
sort of had a thermal equilibrium and casual contact when it was small, and that exponential stretch sort of caused inflation that stretched this very tiny uniform pocket of space by a factor of let's say 10 raised to the power 26 or more in an instant. In an instant, it increased by 10 raised to the power of 26, and this solved the horizon problem that we were facing, and then it hence it sort of what do you say, confirmed or to a limit explained the expansion of our universe. Now this is the whole reason, or the inflation theory, that we base on when we talk about the expansion of the universe. Hope that's clear.
Yes,
And
ma'am.
also, one more thing I would like to add here about inflation theory is the inflation theory also sort of naturally explains why the universe that appears sort of, spatially flat, like, it appears to be flat, or the flatness problem it's called. The flatness problem, which is consistent with the latest CMB data that I'm showing here as well. So it looks like it doesn't have a sort of, a three dimension to it. So this flatness problem is also sort of explained by the expansion theory or the inflammation theory, wherein if you take a side view of this is a very silly sort of conclusion that they've given as well. So if you take a side view of it, you could be seeing a lot more projection to it in space dimension. Please don't consider it as a 3D dimension. It's across the axes. So it is space dimension. In space dimension, we have a lot more that is adding to the fact that it's not a flatness issue we are dealing with here. So this is about the expansion of the universe. Hope that's clear.
Yes, ma'am.
All right. So these topics that I've discussed today are all topics that is having very immense researches happening. So that's why I stressed and took more time in each of these, so that you have some base if you would like to research on it further later. You will have some base on it to go forward with. All right, so moving on, we go to our two activities. First activity is the redshift and the Hubble tension, wherein I would like you to calculate. So you can take up any 2 to 3 galaxies. I will give you the exact number. Maximum two, I would say, yeah, two. I think I haven't mentioned it here, but so take two galaxies and the Hubble constant. So with that, you calculate the velocity. Okay. Uh, you will calculate the galaxy's redshift Z value, whatever galaxy you're choosing. You take up the Z value or the redshift value from the internet, and you use the non-relativistic formula, that is V. Velocity V is equal to C into Z, where C I've already provided. You do the calculation for that, and then you calculate the distance using Hubble's law, where you take distance d is equal to the velocity that you've found divided by the Hubble's constant. Okay. Um, and Hubble's constant, you may have to consider these two, wherein in terms of CMB, the Hubble's constant is this. And in terms of local Hubble's constant, this is the value. Now, you please go out when you check about this activity. Just check what is the difference between, or why is there a Hubble's constant for CMB and why is there a local Hubble's constant. And please make sure that you add one line in your project regarding this. And finally, you just do that for two galaxies. It's probably a 10-minute work to calculate this. And analysis, you discuss the difference in distance results that you get with both the utilizing both the Hubble's constants, and what is Hubble tension implying about the universe's acceleration and dark energy? Now, this is the analysis you need to be writing. Also, along with this analysis, just please mention what you have understood about the Hubble's constant being different for CMB and local. This is your activity one. Okay.
Ma'am, can you just in short repeat once again?
Yes, I will be
And
putting this slide in the group.
about this value of C, ma'am,
Yeah.
the C value is, I mean, you have to take 300,
Yes.
not 3
For
lakh
this
per
case,
second.
no.
Okay,
You take 300 kilometer per second.
okay,
Okay.
okay, ma'am.
Yeah. Because I believe in all the other values, you have kilometer per second considered.
Mhm.
So it could be easier that way. Right?
Okay.
Okay.
And ma'am,
Um,
in short, can you explain once again?
yeah, sure. So what I mean to say is you choose two galaxies of your choice. Okay. Now you go to internet first when you choose a galaxy. First of all, you find that particular galaxy's redshift value, that is value Z. Okay. Now your first task is to calculate velocity using this formula, wherein you have the value of Z that you found from the internet, and you have the value of C given here. Calculate the velocity, keep it aside. Next, you have the distance to be calculated. Now, for distance, you have this formula. In this formula, you have both these. You have V and you have H naught. For H naught or the Hubble's constant, you will be considering both these aspects. For CMB, the H naught is this, and for local, the H naught is this. Now, you need to add a sentence in your project that says, why is the CMB's H naught different from the local H naught? Okay, what you have understood. That is something you have to just quickly have a research on. Finally, you need to give these values as well as write some 2 to 3 sentences about what analysis you have found regarding this question. Discuss the difference in distance results that you're getting, both these. Along with that distance results, you can also write why the H naught is different for both these cases and what this Hubble tension will imply about the universe's acceleration and dark energy.
Okay, got it, ma'am.
Okay, got it? All
Yes,
right,
ma'am.
that's your
And
first task.
so the whole process we have to do it twice for the two galaxies. Okay,
Exactly. But the analysis you can, if
summarize
you
it.
want, you can club it up and write it, or analysis you can write it separately for each galaxy. That's up to you, whatever is convenient for you,
Okay, ma'am.
right?
Ma'am, so will there be any spreadsheet related mentioning two galaxies which each individual student will be choosing? I mean, is
Oh,
there
no, no,
any
no,
case if repetitive galaxies are taken?
no, there is no problem as long as I don't want all of you to be just doing two galaxies. Just when you find a galaxy on your own, just maybe think, okay, this is something different. I'll try to do this.
Okay,
Try to make it a little challenging for yourself. Yeah.
okay, ma'am.
Don't go for the safest option. Yeah.
Yes.
So, yep. So we are going to the task two now, right? So the task two is about this is not calculation at all. This is purely research oriented. Now, this is CMB anisotropy and cosmic geometry. So first off, um, so your goal is to use the CMB power spectrum to determine the spatial geometry or the flatness of the universe that I told the last topic of, right? So first off, you need to identify the standard ruler. Okay, you should research the predicted angular size of first acoustic peak in the CMB power spectrum. So for that, you need to find the CMB. Excuse me. Find a CMB power spectrum and okay, CMB power spectrum should be able to give you the largest sound wave before recombination, and with that power spectrum you should be able to predict the angular size. Okay, the first angular or the acoustic peak that particular spectrum is having. Note that down. It should be a degree, right? It should be a degree. And um I, yeah, it should be a degree, yes. So with that degree in mind, you need to answer the rest of the question, right? So for the model geometry scenarios, for flat, okay, so for the model geometry scenarios, you consider three cases. One is flat universe, closed universe, as in you have a positive curvature, and open universe that you have a negative curvature. You're taking these three scenarios, and for flat universe, you should have your predicted peak size matching the observed size, and your closed universe, you should have the space that is acting like a magnifying glass, making the peak appear larger than what you have found in the first standard ruler. And open universe, you should have it lesser than your standard ruler. Conclusion, you write why do you think this is happening, all three cases, why do you think this is happening, and state that is the cosmological conclusion about the geometry of the universe and how this result will validate the inflation theory. So this is a bit of a research that you have to do. Hope that's clear.
Yes, ma'am.
Okay, so both of these you have over the weekend. You have tomorrow, that is Thursday, Friday, Saturday, Sunday, and your submission is on Monday 10 p.m. Okay, I think the first task should take you less than half an hour maybe, and the second task should take you maybe 1 hour, 1.5 hours maximum. If you're trying to, if you're taking some time to chill in between, 1.5 hours should be perfect. Hope that's okay. All
Yes,
right.
ma'am.
So please make sure that these tasks are completed and uploaded in the drive before 10 p.m. on 3rd, on Monday. Okay. So that immediately after this task submission, I will be starting the minor project too, wherein you have to do a lot more research, because that is a PowerPoint presentation wherein each of you will be presenting for 8 to 10 minutes. So that is something you will have to do a lot of research on. So so let's spare some time there, and once I introduce the minor project to you all, I will be closing the deadline for this, and I will not be accepting any more of these. And unfortunately, I had to do that for previous assignments also. I've told you I've only considered uh, whatever projects you have uploaded till 20, maximum 21st. Whatever has come after that, I'm not able to consider. Okay, because I've already completed the assessment, right? So it's a similar scenario might happen here. Third, 10 p.m. is the last. Whatever comes after that, I may not be able to consider. Yeah, hope that's clear. So minor project 2 will start as soon as we end this. So be mentally prepared for that as well. It's not going to be a big deal. It's probably stuff you can, explain on your own. You just have to prepare a PPT for the sake of presentation. That's it. So that's about it. A big thank you for staying with me for 2 hours. And
For this project, for these two tasks, I mean, we have to combine it in a single Word file or two different Word file or PDFs.
you can have a PDF wherein the first 1 or 2 pages can be about the task one. The second 1 or 2 pages can be about task two.
Okay, in a single PDF.
Yeah, please submit in a PDF.
Okay. No, I mean, not in a separate two PDFs, I was asking.
Not required.
Okay.
Not required. Yeah, because I'll be taking the analysis. I mean, the assessment, the grades or credits for both these together.
Okay.
Yeah, there will be a splitting between the two, but it'll be considered together.
Okay, ma'am.
Okay. Hope that's clear. I'll be putting up the slides for your reference, the activity slides for your reference into the group. You can refer that and you can check that out. If you have any doubts in these, please come back and check with me in tomorrow's session, so you can finish it on time. Because after tomorrow's session, the next session we have is on 3rd. So after clarifying on 3rd, you may not have time to do it, right? So make sure you have a quick look through this tomorrow before the session. just or while we start the session, we have like first 10 minutes of waiting. At least during that time, please just make sure that, see if you can get all the sufficient data that you require, and you can check with me. Hope that's all right.
Yes, ma'am.
Okay. So thank you everyone. Thank you so much. It's pretty late. I think this is the latest we have gone. Anyway, you all have a wonderful have a good night. And yeah, that's all. We'll call it a day and we'll meet again tomorrow. Yeah,
Same time.
same time tomorrow.
Okay.
It could differ by 15 minutes. If there is no session before mine, then it could be 9 o'clock. If there is a session before mine, then it could be 9:15.
It will
Just that
be.
much else.
It will be a
I don't
session.
think, no, I don't think there is a session tomorrow. It's on Friday.
Oh,
But for
okay.
us
Well and good
October
then.
batch, we have a session of aerodynamics tomorrow. That will be probably between 8 to 9. But you can talk to faculty if he is comfortable in taking between 7:30, a little bit
Oh,
prior.
yeah, sure. But yeah, we'll see that. This 11 o'clock is being a little too hectic, right?
Yes.
Uh, I'll do my best to do this. Yeah.
Yes, I'm sure.
Okay. My time is assigned only till 10:15, but it goes way beyond uh because the sections get so much fun. So yeah, I'll try to keep my content shorter tomorrow so we'll have enough time to discuss as well. I don't want to cut down on the discussion, please. So I'll try to keep my content shorter. Yeah.
Okay, I'm sure.
Yeah, because all of us, all the instructors are working as well. So I'm sure a lot of you all are also working. So we all come back home. I have taken 9 o'clock because I reach home by 8:30. So yeah, so that is a problem. So I also have a limit to, check with the other instructors whether they can take it early. So no problem. We'll see. We'll see about it. Yeah.
Yes, I'm sure.
Okay, okay. Thank you so much. Thank you, everyone. We'll call it a day, and all of you take care. I'll also take care. We'll see you tomorrow. Yeah.
Yes, ma'am.
Okay. Thank you. Bye bye.
Thank you, ma'am. Good night.
Thank you,
Good
ma'am.
night.
Good night.
Good night. Good night.